A perfect square. That's what I want to know. Bueller. Bueller. If you don't get that joke, shame on you for not watching Ferris Bueller's Day Off, because that joke is hilarious. Thank you. Come on, guys, wake up. Do we need to do a bunch of jumping jacks or yoga or something? Okay. Kira's like, that will not happen. Come on, I know you know this. We've used this word this year. You've been using this word forever. A perfect square. What kind of a number is a perfect square? 2, good guess. Nope. I appreciate the effort, though. A perfect square.
25?
Yep. Okay, now that you know 25 is a perfect square, someone give me another perfect square.
50.
Nope.
9.
Vest says 9. 25. Someone else besides Vest, give me another perfect square now. 9 and 25. What?
64.
64. We seeing a pattern yet? Okay. Give me more. I saw a couple people shook their head and said no. Okay.
36.
36. 9. 25. 64. These are all perfect squares.
4.
4.
144.
144. Okay. We're getting more now.
81.
81. Okay, someone that hasn't said a perfect square number yet, tell me what is a perfect square. Now that you have some examples, what is a perfect square? You already gave me some of the numbers. I want someone new. Someone who hasn't told me one of these numbers. Look at those and tell me what is a perfect square. So not another example of one. I want to know what makes a number a perfect square number. Taylor, I know I see your hand.
49.
Okay, that's another one. Good. Okay, but I want to know what is a perfect square now. What is it? Yeah, Hayden. That's a good guess. Not a multiple of 4. That's a good guess. The 9 and the 25, those ones 4 doesn't go into that. Taylor, I'm not going to call on you because I know you know because you gave me examples. But I also know more than people. Yeah, Kira.
Is it like multiples of each other, like 2 times 2, 3 times 3, like that?
You got it. Something that times itself, right? I get to a number. So like 2 times 2, 6 times 6, 3 times 3, 5 times 5, 8 times 8, 12 times 12, 9 times 9, 7 times 7. You with me? Better? Okay. So the actual definition of a perfect square is that the square root of that number is a nice number. Because I'm looking for that number times itself. You with me? Okay? So we're going to do something similar like that, but we're going to do it with variables now. Okay? It might sound like it's going to be harder, but I actually think it's a lot easier because it doesn't matter if you know your times tables. We've talked about times tables a lot this year, right? What's the purpose of memorizing times tables? It's to be fast. Well, Summers doesn't care if you're fast. I just want you to get questions right? That's why I've got a pile of times tables in the window back there by the calculators. You can use them anytime, right? But a lot of times people struggle at math because they don't know their times tables. Well, if I do this idea with variables, then it actually is easier because I don't have to worry about if I know what numbers multiplied together, okay? So let me show you the idea of a perfect square another way. If I had the square root of 7 squared, okay? Why does addition cancel out subtraction? They're inverses of each other, right? They cancel each other out. They're opposite, right? Okay, that's the same idea with a squared and a square root. So one of the reasons why the square root of 49 is 7 is because the squared and the square root cancel, okay? Because I have 2 7s because of the exponent, And I want 2 of the same number because of the radical. Okay? I want you to think about that. We're doing okay? Anybody? Questions so far? Peyton, you good? Yeah? Okay, so I want you to look at number 1 here, okay? I have 3 n's, right? Is that fair? That if you ignore the cube root, do you guys know what a cube root is? Do I need to talk about that first? No, you don't know what that is? Okay. You know how in math, every operator, everything in PEMDAS has like an invisible number? Like when we were doing exponents last time, if I asked for the invisible exponent, it was a 1, right? Good. If I wanted to know what coefficient was on x, the invisible multiplication number is also 1. Right? Everybody okay? Okay. Darius, Landon, Ethan, you guys good? Yeah? Okay. The invisible addition number is 0. Okay? This symbol right here, a square root, like the square root of 25 is 5, or the square root of 49 is 7. The invisible number on roots is a 2. So if there's nothing there, I can assume it's a 2. Every math thing has an invisible number. Sometimes it's called the identity, but it's like the one that we use most often, so we try and be a little lazy and we don't have to write it. You guys like being lazy, right? You're teenagers. Yeah? No? Nothing? Tough crowd? Cool. Totes. Okay. So anyway, when I don't see anything, it's a square root. If I do see a number there, okay, so like on this one, instead of looking for 2 of the same number or letter or whatever, I want 3. Okay? We doing all right? Everybody okay? So I want you to look at the idea of me looking at, I want 3 of the same thing. And then this tells me that I have 3. We doing okay? So these cancel. And that's called a perfect root. Because the number that I want is the same as the number that I have. We doing all right?
What does the left arrow say? You can't see it on the screen.
Oh, sorry, want. Want 3 and I have 3. Okay? So like what we talked about over here, if I wrote that a little different, I'm just going to erase this just to have more room. The square root of 49 says I want 2 of the same thing. And 49 is that I have 2, because it's 7 squared, right? So the root, okay, that's that weird symbol that kind of looks like a long division sign, tells me how many I want, and the exponent tells me how many I have. We doing okay? Now, not all radicals are perfect, though. So let's look at number 2. I want 5. Is that fair? If you look at the radical? But how many do I have? 8. So it's almost like I have a factor tree here where I have 8 m's. But I only want 5 at a time. So really, what if I thought of this 5th root like the 5th root of m to the 5th, and And then the fifth root of, how many would be left over that didn't meet the 5 requirement? 3, right? Everybody okay? Do either of those things simplify? The first one does, right? Because I want and I have the same amount. So the final answer on number 2 would be m, 5th root of m cubed. Because I can't take any more groups of 5 out. We're going to do a bunch of these today. This is all we're doing all day. So if you don't get it quite yet, that's okay. Anyone have any questions so far? Let's try one more together. Maybe 2 more because 4 is weird. And then I might have you try one, okay? I want groups of 3 on number 3, okay? Vess, can you put your book away? And Landon, can you wake up? Yeah. It's the most boring lesson ever, I know. I put you to sleep with my quiz earlier. You're welcome, okay? Some of you needed that nap today. I'm sure you're up all night playing Fortnite or Minecraft or something. Are those still popular games or no?
Yeah.
Yeah? Oh, well, good. I want groups of 3. How do I know that? How do I know I want groups of 3? Yeah, very good. The little 3 on the root. Okay? But I have 7. So in my 7 branches of my factor tree, how many groups of 3 do I end up with? 2. 2 groups of 3. You with me? I have one here. And I have one here. So I end up with the cube root of p cubed times the cube root of p cubed times the cube root of p. Do you see how I can account for all 7 of my p's there? But let's pause for a second. If I gave you x plus 1 equals 5, you don't have to write this down, I just want you to look. And I minused 3 from both sides, would that be a smart thing to do? No, because things only cancel. Not only do you have to do the opposite operation, but don't the numbers have to be the same too? So addition and subtraction are inverses, but if this one is a plus 1, then this one has to be a minus 1, right? So that's why over here, the only ones that cancel are the ones that the numbers are the same. So I end up with p times the cube root of p, but we learned last unit, how does p times p simplify? P squared. Okay, I want to do number 4 because it's a little weird. How many do I want to group together? How many do I want? 2. Okay, good, 2. How many do I have? 1. So can I make any groups of 2? No. Okay, I want you, let's pause again, because sometimes if we do things you're more used to, you don't have to write this, I just want you to look. If I asked you, we're pausing so I can explain what's going on with 4. If I asked you to reduce 5 over 10, that fraction, you can reduce that, right? That reduces to 1/2. Is that fair? What if I asked you to reduce 1/4? If I asked you to reduce that fraction, what would you tell me? You can't because it's already as small as possible, right? So if the want is bigger than what I have, then guess what? It's already as small as possible. That one was done. It was already reduced.
Does that mean 6 is also just done?
Very good. Let's look at 6. Taylor says that I want 5 to make a group, right? But I only have 3. So Taylor's prediction was that one's already reduced also. You guys agree? Me too. So that one is already reduced. Instead of reducing fractions, what we're doing is called reducing radicals. Okay? I am going to walk around and help, but I want you guys to just try 5, 7, and 8. And then we'll check answers. 5, 7, and